We should start. Next speaker is Matti Jarvinen from APCTP. He will give us talk about how hydrodynamic picture of domain velocities. Would you please start?
Thank you. I hope that you can hear me well. First of all, I would like to thank the organizers for inviting me to give talk on my work. And I will focus on this first paper, which will soon appear in PRL, but I will say also a few words about the earlier work. And so the outline of the talk is as follows. I will start by introduction and motivation. Then I will discuss in more detail deconfinement, transition, and domain walls, particularly in the Witten's model. And then I will go on and discuss moving domain walls and derive this formula for the domain wall velocity, which then later in the talk will be compared to some simulation in a holographic non-conformal model. And if I have time, I will also discuss this improved formula and walls of nucleated bubbles, and then I will summarize. Okay, let me anyways start by introduction and motivation. Oops. Looks like, okay. So first order phase transition and domain walls are a fundamental topic in physics. And well, for this talk, the main motivation comes from strongly coupled field theory. So there are two examples. There's QCD. At zero chemical potential, there's a crossover, but at finite density, there is conjectured first order phase transition, which could be broken in heavy ion collisions and is also important for neutron stars and neutron star mergers. But then you could also have a strongly coupled extension of the standard model, which could drive a first order phase transition in the electroweak or in some hidden sector. This could lead to some bubble, this first order phase transition could take place through bubble nucleation in the early universe, and it could give rise to gravitational wave production that could be detected by the LISA gravitational wave observatory or some of its successors. And well, basics of domain walls. When the temperature is close to the critical temperature, you expect to have static domain walls. So you can have, you have first order phase transition and domains of coexisting phases separated by a domain wall. And pressures on both sides are balanced and the domain wall is static. But if you drive the temperature away from the critical temperature, for example, then you expect a more moving domain wall. And there are different cases. You can have nucleated bubbles of stable phase within a supercooled medium, like you expect in the early universe. You can have an interface between phases away from the critical temperature, but at same temperature, or an interface between phases at different temperatures. So, and you expect that there's a pressure difference over the domain wall and it starts to move. So naively, you would expect that such a pressure difference gives rise to an accelerated motion, but well, typically what happens actually is that the acceleration stops and the domain wall approaches a constant velocity. And the common law is that there is some friction force which balances the pressure difference, and this friction force is challenging to calculate. You need some non-equilibrium stuff. But actually, it turns out that at strong coupling, as I will show you later in the talk, this domain wall velocity and the picture is much simpler. So you can get the domain wall velocity just by using the equation of state and hydrodynamics. But actually, this takes me already to the second part of the talk where I discuss deconfinement, transition, and domain walls. And the main one of the basic example of a holographic theory with a first order phase transition is this Witten model. We will actually be using a lower dimensional variant of this Witten model. And the basic idea is that, well, you take a theory with one like extra spatial direction, and then you compactify it in a circle with antiperiodic boundary condition for the fermions. And at low temperature, you expect that the bulk geometry is such that this compactified circle closes off into a circle, CCAR, in the holographic direction, as I sketch here on the left. So this axis here is the holographic coordinate, and at the as you can see, the phi in the phi direction, you have this cigar geometry. So this is this called solid geometry, and this gives rise to a confinement on the field theory side. And in the high temperature, you have an analogous configuration where instead of the phi coordinate, the geometry of this Euclidean time component closes off to a cigar. And this is a black brane solution, and gives rise to a deconfined phase on the boundary. And between these two geometries, you expect to have a first order phase transition. And this means that there is also a domain wall solution. And this has been constructed in the literature already many years ago. So these people constructed a static planar domain wall solution interpolated in between these two phases. And well, this is actually a highly non-trivial task because there is a topology change between the two phases. But I'm not going into the details, but anyways, by making a well-motivated choice of coordinates, you can construct a solution which interpolates between the soliton at low temperature side and the black brane on the high temperature side. Everything at the critical temperature. And we will be studying the solution which has 4+1 dimensions, so which is dual to the true 3+1 dimensional boundary theory with one compactified coordinate, so that the flat quantum field theory has 2+1 dimensions. And well, now that you have the geometry, you can look at the basic properties of the field theory and the boundary. And this is you can in particular extract the energy momentum tensor over the domain wall. So here I'm, well, basically as for the energy density, you can study this difference between the components of the energy momentum tensor in the time direction and in the compactified direction. And well, this is basically what gives you the profile of the energy density. And this, as it turns out, well, there are two curves in this plot here on the right. There is the data from the numerical solution of the geometry, and then there is this fit by the hyperbolic tangent, but you cannot see, you only see one curve because they are right on top of each other. So you can fit the data with this hyperbolic tangent with extremely good precision. And the only additional feature which the data has is that there is a bump in the remaining, this y component of the energy momentum tensor, which is the direct, y is the direction parallel to the domain wall. But all the rest is fixed by the conservation of energy momentum tensor and tracelessness. And this bump can be fit also by, well, these sort of combinations of this tan profile. And you can see, well, this is one of the fits. It's also very good. By the way, this tan fit actually turns out to work in non-conformal holographic models, but it's not quite as good. Well, I'm motivated by this kind of fitting. In this earlier paper, we came up with a hydrodynamic Lagrangian, which can realize this good fit of the energy momentum tensor. And it turns out, well, that the Lagrangian, which you can write down, is like this. So basically there is a term which just covers the hydrodynamics, and then there is this term governing this an extra scalar field gamma, extra scalar field gamma, which is well, gives you the dynamics of the domain wall. And it turns out that there are two options which are like correspond to these two ways of fitting the T mu nu of the solution. So you can make either a choice where this capital gamma on the hydro side is exactly the small gamma, and this a function which multiplies the second term is this more complicated function. Or then you can make another choice where you have a non-trivial map in between the two gammas, and this a function is just a constant. And with this, well, here I should say that the pressure is just the standard Lagrangian for simple hydrodynamics. Anyways, but with this Lagrangian, you can realize the precise fit of the thermodynamics. So this order parameter gamma, which was just obtained in this fit, is in this Lagrange is promoted into a dynamical field. And this coupling of the gamma to the hydrodynamics, which is included in this term, also turns out to be natural, and it will lead to an asymmetric effective potential. Or the coupling to hydrodynamics will just give you an asymmetric effective potential for gamma when the temperature is close to Tc, apart from the symmetric term, which is already included in the action. And well, why do we do this construction? Well, doing time-dependent solutions in Witten's model is extremely hard due to this topology change. Well, there are some results in the literature, but it's very complicated. However, but since we have this hydrodynamic model, it's actually relatively easy to do time-dependent solutions, and this is actually what we will do. So we will use this hydrodynamic model, actually of this option B, to do time-dependent simulations for the more moving domain walls. And this actually takes me to the third topic of my, or third section of my talk. So we took this a domain wall. You would expect what you would be. So we took a domain wall and just went to a temperature which is higher than the critical temperature and saw what happens in this hydrodynamic model that we have. And you might expect that there is this domain wall starts to move, and the first accelerates and then later propagates at constant velocity. But actually what you see in the simulations is quite different. So I'm here plotting the pressure and the momentum density that you obtain from our simulations as a function of the position over the domain wall and the time. And you see that it's quite different from the naive expectation. I mean, there is something like a domain wall movement, but there's more complicated dynamics. So what is going on? Yeah, so you can identify that indeed, as expected, the domain wall, which is here, this valley, will move to the right. And it will, at late times, move at constant speed. So this is what we would expect. But you also see that there is some non-trivial dynamics happening here on the left side of the domain wall. The most prominent feature is this hydrodynamic wave which propagates to the left. And if you look at the pressure, there is essentially no pressure difference over the domain wall, which is perhaps a small surprise. All the pressure difference takes place over this hydrodynamic wave, which is moving to the left. And between these two waves, there is a plasma moving to the right following the fall. So there is a non-trivial momentum density describing it. So there is a lot of motion to the right here. And so the schematic picture of what happens can be obtained. So the full picture can be obtained by gluing together two elements. So there is this domain wall moving to the right, and there is no pressure difference. And this actually, this domain wall just turns out to be pretty much exactly the static domain wall boosted to a finite velocity. And then there is this hydrodynamic wave moving to the left, and this supports the pressure difference. So this is what we got from the simulations. And well, as it turns out, now you can analyze the hydrodynamic. Well, we know exactly what this domain wall here, it's just a static domain wall boosted. So you can then analyze the hydrodynamic wave. And this should interpolate between a static plasma with high pressure and a plasma with pressure exactly the critical pressure, which is moving with the velocity of the domain wall. And because the wave is deep in the deconfined phase, this is the part of the solution of which in our hydrodynamic setup is described in terms of perfect fluid hydrodynamics only. So there is no degrees of freedom coming from the additional gamma field in this region. And because the fluid velocity in between is exactly the same as the domain wall velocity. So this the fluid here in between is just following the domain wall. Its fluid velocity is exactly the same as the domain wall velocity. We can just access this domain wall velocity through this hydrodynamic computation. So we just need to compute what is the velocity of the fluid by computing the solution of the hydrodynamic wave. And the solution for this hydrodynamic wave turns out to be what is called the simple wave in Landau-Lifshitz. So you assume that the hydrodynamic quantities are functions of a single variable, for example, the pressure, and you just plug this into like your perfect fluid hydrodynamic equations. And I'm not going to show you the computation, but from that there you can derive a formula for the domain wall velocity. It's given by this kind of integral. So the only input which you need here is the equation of state, and then you can plug it into this integral and do the integral and compute the domain velocity. And well, now we would like to compare this the predictions of the formula to Witten's model, but it's not. It turns out that these simulation results are not precise enough to do a detailed comparison. So instead, we will use a different holographic model. So this will be this holographic non-conformal model. And this is defined in the bulk by a gravity plus scalar system, which has 3+1 bulk dimension. So it's dual to 2+1 dimensional field theory. Field theory at the boundary. And this potential for the scalar is chosen in such a way that there is a first order phase transition. So here I'm showing the rescaled entropy as a function of the temperature, and you see that indeed there's a first order phase transition. And well, in this system, the phase transition is just between two black hole phases. So there's no topology change, and you can quite easily do numerical simulations directly in the gravity model. Results from these numerical simulations for the same kind of setup as earlier is quite similar in the Witten's model, but there are also some small differences. Now the profiles are smooth, so if you recall in the Witten's model, there were some waves here, and we think that this is just due to finite dissipation, because in this non-conformal holographic model, you have all the dynamics included, including the dissipation. And instead of empty space, now in principle, we also have some fluid moving here in the low temperature slide in this region. And there are some different fluid velocities on different side of the domain wall. So it's not exactly the boosted static domain wall, but you can actually show that the good approximation it still is. So basically the fluid velocity in this low temperature phase here is small, and the velocity between the domain wall, fluid velocity here is actually close to the velocity of the domain wall. So basically this means that you can just do the same analysis as in the Witten model, or what I was sketching earlier. So you just compute the hydro over hydro solution of this moving wave, and from there you can get the domain wall velocity. So you just apply the formula as you expect. And the result is shown here. So as a function of the pressure difference, we obtain different values from the numerical solution for the velocity of the domain wall. And this is compared to the result from our formula. And you see that in particular for low pressure differences, there is a very good agreement between the results. But you can actually then study also a setup which is closer to what you would expect in the early universe. So apart from taking the system to just a temperature which is higher than the critical temperature, you can study a nucleation of small domain of stable matter within a supercooled phase. So you prepare the whole system in a supercooled phase and put in a small bubble which starts to expand. And it turns out, well, this is the simulation result is shown here on the right. So I'm showing as a function of the position and time the hydrodynamic velocity of the fluid. And this is correspond to the so-called, for the experts, this is called the so-called evaporation case of the bubble nucleation. And inside the bubble, the fluid will eventually be roughly at rest. Yes, as you can see from the simulation result. And as well, I'm not showing the pressure difference here, but you can show that, okay, so this here is the now the domain wall, and the pressure difference over the domain wall is again close to zero. So the pressure difference is still coming from this hydrodynamic wave moving to the right here. And well, it turns out that in order to compare to the simulation result, in this case, you need to upgrade the formula a little bit. You can use the fact that, as you saw from the simulation result, the inside the bubble, the fluid will be at rest. And this means that you can just you can compute this low temperature velocity, the velocity in the low temperature phase, instead of it just ignoring the computation.
Some simple question.
Yes.
So when you also consider the bubble, so the bubble is infinitely big size, because if bubble is smaller than the critical size, it may shrink away rather than expand.
Right. Yeah. Okay.
Since
I should tell you, this is not really a spherical bubble. It's just it's a planar bubble.
So in that sense, it's an infinite size.
Yeah. It's which corresponds to infinite size bubble. Because because we could also do the spherical simulations, but they are a little bit more complicated. So for this first study, we only did the planar case, which, as you say, it corresponds to an infinite, like sphere with infinite radius. Anyways, using this information on the low temperature phase velocity, you can plug it into the hydro computation. I'm skipping all details. This gives rise to this correction factor, where the subscripts L and H refer to the low and high temperature phases. And with this corrected formula, you can again compare to the simulation results for the domain wall velocity as a function of the pressure difference, but now in this bubble nucleation case. You see that it is improved formula. This correction is important in particular for larger pressure differences. So this improved formula does a better job at larger temperature pressure differences. Anyways, this was everything I wanted to discuss today, so I will just summarize. So we established a simple hydrodynamic picture of domain walls for a range of strong coupled theories, basically holographic strongly coupled theories. The main result was that we obtained a simple formula for the domain wall velocity in terms of the equation of state and perfect fluid hydrodynamics. And this result applies to interfaces between phases at different temperature, systems at constant temperature away from the critical temperature, and to this expansion of nucleated bubbles in a supercooled phase. Well, our computation for this derivation of the formula, we actually didn't use any holographic input. It was just hydrodynamics. But using holography was crucial to motivate and to check the validity of the formula. The picture arose by composition of this boosted domain wall and a hydrodynamic wave. And this what was important was that this hydrodynamic wave accounted for the pressure differences, which allowed us to analyze and compute the domain wall velocity. And the pressure around the domain wall are almost balanced, and it's close to the critical pressure. Okay. Thank you.
Okay, let's thank Matti Jarvinen for a very interesting talk. Are there any questions? I think it's not. So then, yeah, let's thank speaker again, and thank you very much.
Yeah, thanks again for the invitation.
Okay, Matti